Have you or a family member ever been personally victimized by optimization?
Yeah.
If this little boy resembles you in any part of calculus class, please call the number at the end of this video, as you may be entitled to compensation for your troubles that you go through every single day being an AP Calculus student.
Well, I'm Jake.
I'm Bianca.
And I'm Avery. And we're here to make you feel less victimized by optimization.
Me?
Not you.
This is the AP optimization problem that our group chose to demonstrate to you.
Alright, so this is the equation that we have for the problem. And so when y has to equal 0, so when the ball hits the horizontal axis, we set it equal to 0. So when we do that, we solve for x, and we get x is equal to 1,000 m over e to the 2m.
To maximize x, we have to take the derivative of the equation that we just found and set it equal to 0. So when you set it equal to 0, and you take the derivative using quotient rule, you get 1,000 times e squared m minus 2e squared m times 1,000 m over e to the 4m. After you do this, you need to solve for m to find the slope. You will do that by first factoring out the 1,000. So you have 1,000 times e to the 2m minus 2e 2m times m over e to the 4m. Next, you'll cancel out e to 2m. Leaving you with 1,000 times 1 minus 2m over e squared m. This is all still set equal to 0, and you can manipulate the equation now to get m by itself by moving the e squared m to the left, which cancels that out, and the 1,000 to the left, which cancels that out. You're left with 0 equals 1 minus 2m. And then when you add 2m to the left, and then you get m by itself, and you're left with m equals 1/2. And that's your slope for x being maximized. Next, we have to prove that 1/2 is actually a maximum, and to do that we're going to use the first derivative test. This problem uses an interval of 0 to infinity because it's dealing with distance and time, and neither of those can be negative. So our 0 here is going to be 1/2. Anything to the left of 1/2 in this problem is going to be positive, and anything to the right is going to be negative, proving that this has to be an absolute maximum.
Action. So for part B, we want to maximize y and find the greatest height the ball will hit on a wall 100 feet away. So the wall being 100 feet away, x is going to equal 100. So we're going to plug 100 back into our original equation for each x. So then that leaves us with y is equal to 100 m minus e to the 2m over 1,000 times 10,000, because 100 squared is 10,000. So after we do this, we can simplify a little bit. We take 1,000 out of both of these. So 1,000 cancels out on the bottom, and that leaves us with 100m minus 10e to the 2n. So now we have this equation, and to maximize y, we have to take the derivative and set that equal to 0. So dy over dm is equal to 100 minus 20e to the 2n. So now, since we found the derivative, we can set this equal to 0. 0 is equal to this. And then we're going to solve it. Divide both sides by 20. And that'll leave you with e to the 2m is equal to 5. Now to solve for m here, we're going to take the natural log of both sides, cancel out the e. That cancels that, so we're left with 2m is equal to natural log of 5. So now to maximize y, you're just going to divide by 2. So then m is equal to 1/2 natural log of 5.
So to prove what we got for part A, we have created a graph on Desmos and plugged in the equation in the problem and created a slider for m. And as you'll see, as it comes back down, we'll stop it here for you at 0.5. You'll see that the ball is the furthest away from the origin when m is equal to 0.5. So this right here proves that 0.5 is the correct answer for part A. So we did the same thing for part B. And in part B, it's asking how high the ball hits something 100 feet away when you throw it at that something, kind of like this. Maybe that something they said to throw it at was a wall. Nevertheless, you'll see that it strikes the highest point on this ball at 1/2 natural log of 5, or better known as 0.805. We're sorry to inform you, but there is no optimization hotline for you to call. However, we recommend the fetal position in a dark room to soothe your troubles with optimization. Thank you for watching this video, and hopefully we have enhanced your knowledge in the world of optimization.